Okay, so this video is going to be on solutions to homework problems 11-50 and also 11-57. So let's start with 11-50. So this problem is another double pipe heat exchanger. So we'll diagram what that looks like. Okay, so what we're told is that we have this double pipe parallel flow heat exchanger and it's used to heat cold tap water with hot water. So they're givens for the problem. Okay, we are given the CP of the hot water, and that's equal to 4.25 times 10 to the third joules per kilogram. We are also given the temperature coming in of the hot water, so T hot 1 is 85 degrees Celsius. We're given the mass flow rate of of the hot water, and it's 1.4 kilograms per second. We're also given the exit temperature of this hot water, T hot 2, and that's equal to 50 degrees Celsius. All right. Aside from that, so I'll draw this in the diagram. We have a parallel flow heat exchanger, so there's flow of hot water going through this pipe, and the outside annulus, we have cold water flowing in the same direction. Okay. So we have T hot 1, T hot 2, T cold 1, T cold 2. Okay. We're also told that there is a loss of 3% of the system. So we can interpret that as there's an efficiency of 0.97. So we find the total heat transfer, and we know that 3% of that heat is not transferred to the cold fluid, but instead is lost to the environment. We're also told the coefficient, the overall heat transfer coefficient of this heat exchanger, capital U, is 1150 watts per meter squared Kelvin. And we're told that the surface area is equal to 4 meters squared. And it asks us to find two things. It says determine what the rate of heat transfer to the cold water is. So what is the Q dot to the cold water? And also determine what the log mean temperature difference is. So let's begin. Our heat exchanger analysis, we know that the Q dot, or the heat transfer rate, is equal to m dot times Cp times the change in the temperature. Okay? So we have the mass flow rate of the hot water. We have the Cp of that hot water. So we'll just look at the temperature difference of the hot water. But we know that only 97% of that is getting transferred to the cold water. So we'll multiply this by eta. So we know that mass flow rate is 1.4, Cp 4.25 times 10 to the third, and the temperature difference of the hot water, we have 85 degrees Celsius minus 50 degrees Celsius, and then we multiply that by the efficiency of 0.97. And this gives us that the heat transfer rate is 2.02 times 10 to the 5 watts. The next thing it asks us, so that's part A. The next thing it asks us is what is the log mean temperature difference. So we know that for heat exchangers, we have this equation that looks like Newton's law of cooling that says that heat transfer rate is equal to the overall heat transfer coefficient of the heat exchanger times the surface area times the log mean temperature difference. So now we know what Q dot is, 2.02 times 10 to the 5. We're given the overall heat transfer coefficient, 1150. We know the surface area also given to us is 4 meters squared, and therefore we only have one unknown in this equation, and that's the log mean temperature difference. So we can just solve this equation for the log mean temperature difference, and we will get that that is equal to 43.9 degrees Celsius. Okay? So that was number 11-50. The second problem that we're going to look at is 11-57. And this is another double pipe heat exchanger, except this time it is a counterflow. And there is engine oil that's going to be heated from 20 degrees to 60 degrees. So again, we have this double pipe heat exchanger. Okay. But now we have going through the inner pipe is oil. And then in the outer annulus, we have steam that's condensing. So steam, and it's at 130 degrees Celsius. And because it's condensing, we know that all of the heat goes into changing the phase of the fluid, and therefore the fluid will come out at the same temperature, 130 degrees C. Okay? So the oil is being heated as it goes through, so it comes in at 20 degrees Celsius, and it leaves at 60 degrees Celsius. So we'll start to jot down all of our givens. We know the m dot of the oil is given to us, and that is equal to 0.3 kilograms per second. Cp of the oil is also given to us. That's 2100 joules per kilogram Kelvin. We're given the diameter of the pipe. That's equal to 0.02 meters. T cold 1, 20 degrees C. T cold 2, the oil comes out at 60 degrees C. Then we know that T hot 1 is equal to T hot 2, and that's 130 degrees C. Right? So these two temperatures here we're going to call 1, and these two temperatures here are 2. Okay. We also know the latent heat of vaporization is 2174 times 10 to the third joules per kilogram. We're given the overall heat transfer coefficient. It's equal to 650 watts per meter squared Kelvin. We are asked to find two different things: what the heat transfer rate is, and also we want to find, or we want to size this heat exchanger and determine what the length needs to be. All right. So let's get started. So we know the heat transfer rate is just going to equal mass flow rate times Cp times delta T. So we have all of these values for the oil. So oil, oil, and delta T cold, because the oil was our cold stream. So we know that this is equal to 0.3 times 2100 times delta T cold is 60 minus 20. So we get that our heat transfer rate is 2.52 times 10 to the 4 watts. Okay. The other thing we know is that this heat transfer rate is also equal to U, the overall heat transfer coefficient, times the surface area times the log mean temperature difference. So this is going to equal U times the surface area is just 2 pi times R times L. That's the surface area of the tube. And the log mean temperature difference is just delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2. Okay, we can start to plug in. Q dot is 2.52 times 10 to the 4. U is equal to 650 times 2 pi times the radius is 0.01 meters times L times delta T1 is 130 minus 20 minus delta T2 130 minus 60 divided by the natural log of delta T1 130 minus 20 divided by delta T2 130 minus 60. So now we have one equation, one unknown. We can solve this for L, and we get that L is equal to 6.97 meters. Or we can just round that and say we need a 7-meter long double pipe heat exchanger. So we have officially sized our heat exchanger, 7 meters. And those are the two answers.